All right, so quick about me. I'm a fifth-year PhD student in stats at NC State. I've been using Julia for the last 2 years. And so part of this is I basically am doing all the implementation version of my research into this package, Online Stats, which is statistics for streaming data. And then I just kind of manage a couple other toy projects in my spare time. So average shifted histograms is basically kernel density estimation with a fine partition histogram. And then I have a sparse regression package, which is basically like GLMNet, but it has a few other models and uses a different algorithm. And then a few other kind of toy projects that I like working on. All right, so I'm going to talk about what is Julia. So many of you probably went to John Pearson's tutorial the other day. So some of this is going to be review for those of you who went there. And then why would we use Julia? What is the current state of Julia for statistics and data science? How can I use Julia alongside my favorite stuff in R and Python? And then which Julia packages provide unique features. So I kind of came up with a short list of like what are the cool things going on in Julia that I have not seen elsewhere. So I'll kind of end with that. All right, so from the website, Julia is a high-level, high-performance dynamic programming language for technical computing with syntax that is familiar to users of other technical computing environments. So it has this collection of great features that makes it work really fast. And the developers kind of say they can't just take the magic dust that makes Julia fast, you can't just sprinkle that on some other language because they have this set of features that work really well together, and that's how they get performance. So a big part of this is the JIT, so this just-in-time compiler. So your code is compiled right before it's run. And this works in combination with this great type system and type inference. And I'll talk quite a bit about multiple dispatch. Another great feature is macros, and these are metaprogramming tools. So you write code that writes more code. So they're essentially functions of expressions. And so macros alter your expression before the code is actually run. And there's a whole lot of powerful things you can do with that. And then also arguments passed by reference into functions. So if you're working with very large matrices, you can update things in place rather than making copies. And you can get a lot of performance gains that way. All right, so this is showing the JIT in action here. So the mean function in Julia is written in Julia. And so that's one kind of cool thing about Julia is that so much of it is written in its own language. So the mean function, the first time you call it, it needs to actually get compiled. So I'm using this @time macro, and again, so this is basically getting the timestamp before and after, looking at the difference. It also tracks the number of allocations that function does, and then the total number of allocations taken. So the first time you call it, you might be a little taken aback, like why is this simple mean function taking a megabyte of memory? But then when you call this function again, it just calls the compiled version, and you get good performance there. So that's the JIT. So Julia is both dynamic and compiled. So here is a quick example. So I can write a generic function, just f of x equals x squared. And I'm using this code LLVM macro to take a look at the code that's getting sent to the JIT. And the details of this aren't too important. But so I'm giving this function in int64. And Julia is compiling a method specific for int64 types. Whereas if I give my function a float 64, it compiles a method specific for doubles. So this is really cool. So you only really need to worry about types if you want to. You still get this optimized code, even though I have not told Julia anything about the type information. So this is the power of type inference and the JIT at work here. All right. So the Julian way to do things is programs are organized around multiple dispatch. And this is just a way of saying that functions call different code depending on the types of the arguments that you give it. So a great example here, I think, is in the distributions package, which is one of the more mature Julia libraries. But so with multiple dispatch, you basically define like the right terms of you want to happen. So here's an example. So distributions are types in the distributions package. So I'm just making a gamma 5.1, normal 0.1, and a beta. And then I'm evaluating the CDF of these three distributions at 0.5. So this is I'm coming from the R world. So this is a big contrast to R. So in R, you have like a P gamma and P normal, P beta functions. So that's something you should never do in Julia. So kind of rather than, polluting the namespace a little bit, in Julia, you come up with the right like verb or the right name for your function. And then you define different methods depending on the types that you give it. All right, so I'm going to go over an example of just like the power of writing, generic code in Julia. And it's typically not a whole lot of extra work, especially if the abstract type structure has been well thought out. So I'm going to go over just a very naive quantile algorithm using Newton's method. So univariate distribution is an abstract type defined in distributions. Basically, I know any concrete subtype of univariate distributions has a method for mean, PDF, and CDF. And so we'll just glance at this upper function here. So here I'm actually annotating the type. So now I want to enforce that the user is providing a univariate distribution, and then I'm giving it a number. So basically I want to solve the CDF at theta equals Q, and that's how we define our quantile. So here is our Newton step here, and we can see like I'm passing D through, and D needs to have a method for mean, a method for CDF, and a method for PDF. And this thing is going to work. So I've defined this only one time. I haven't done anything specific, but this kind of immediately works for gammas, normals, and betas, or any other univariate distribution I throw at it. So if I wanted to do this in R, I would basically, so this I think is about 10 lines of code. So if I were to do this in R, I would have to write 10 times as many distributions as I would want to cover to do this algorithm. So this is the power of abstraction. You just save a whole lot of lines of code, and because of the JIT, we still get great performance out of these things. So it's just a really, really cool tool. All right. So why kind of like was I originally interested in Julia? So even besides kind of the cool performance stuff it gets, it's free, it's open source. Most of Julia is written in Julia. So this is awesome just because it's so much easier to find out what's going on. So again, coming from R, if I want to figure out what something's doing, I'm often, ending up looking at C++ or Fortran code, whereas in Julia, I just find myself writing or looking at Julia code. And to the same extent, so this means writing Julia gives you expertise in Julia development, which maybe sounds pretty straightforward, but if you're a heavy R user, that doesn't really make you proficient to write R packages, because to write a good R package, you need Fortran or C++. Whereas in Julia, you're getting performance out of Julia, so the more familiar you are with it, the more capable you are of writing a code for actual packages to release to the public. Yeah, and so this is the idea that there's no two-language problem, which comes up a lot when you hear people talk about Julia. But the idea is that prototype code goes into a high-level language like R, and production code goes to a low-level language like C++. So why we're using Julia is because there are major wins for language that lends itself to both prototype and production code. All right, so what is the state of Julia? So here's a plot of the number of tagged packages over time. So if you look at July of 2015, we're sitting at about 600, and a year later we're at about 1,000, so not quite doubling, but a pretty strong rate. And then if we look at the number of stars on GitHub over time, we can see a year ago we were at about 8,000, and we're now currently, 17,000 or so. So I see this as a good indicator that the stars are growing at a faster rate than the number of packages, just because I see the number of packages, as a bad measure of the number of contributors, and stars as a bad measure of the number of actual users. So it's good to see that users are increasing at a faster rate than contributors in some sense. So are people taking Julia seriously? So obviously I think yes. And so here is just a couple, of examples that I kind of thought about. So the New York Fed has this model originally in MATLAB, DSGE, Dynamic Stochastic General Equilibrium Model, which they moved over into Julia. It's apparently a lot of people use this. I'm not completely familiar with it. But getting the attention of like the Fed, I think is fairly significant. My advisor works on a project called Mendel, which is statistical analysis for genetics data, mostly SNP data. So they're transferring this gigantic code base, something like 60,000 lines of code of Fortran, into Julia. And so I'm guessing it's going to be considerably less lines of code once it's all in there. But it's a significant undertaking, and just the fact that they've chosen this kind of like new open source thing. So they originally just kind of releasing executables, but now they're just going to have this completely open source Julia project. Julia's also gotten the attention of Intel Labs, so they're working at a couple other projects that I thought about, where this high performance analytics toolkit, hpat.jl, which to my understanding is a competitor to Spark. They give some really impressive benchmarks on their GitHub page. I don't know how true those are, but they say they beat Spark in logistic regression, at least in the example they have. And then the parallel accelerator packages, which does some cool parallel accelerations. Also, this arbitrary ranking system puts Julia now in the top 50. So I think it's silly to rate languages a little bit, or like rank them in a list, because they do completely different things. But so Julia is now 47 on this PyOV index. So I don't know if that actually means anything, but it's nice that it's at least getting a little bit of attention. All right, so specifically, so what are the tools for statistics and data science? So if you're a heavy user of stats and data science tools, you want to take a good look at this Julia Stats organization. So StatsBase kind of covers a lot of the functionality in R. It provides like a sample function if you want to sample various values out of a vector. StatsBase provides that. It also provides a lot of generic abstract methods for things like model fitting. And so it defines part of the correct language in order to analyze statistical models with, but it doesn't actually implement any of these like fitting algorithms. So in StatsBase, it defines like a fit method and like a few other methods like specific for linear models. And then there's packages like GLM here for generalized linear models, which basically implements this abstract definition in StatsBase. And so I mentioned distributions before. And yeah, I definitely think that is one of the more mature libraries in Julia. It's very, very cool. Use it all the time for stuff. But again, it's just you pick kind of the right interface on how to handle distributions, and then you come up with this correct interface, and then you like automatically know how to get the PDF or the log PDF of some distribution. So data frames is also similar to pandas. It's recently undergone some pretty big changes. So I think just recently there was a PR that just got pulled in. So now nullable arrays is now kind of the back end for data frames. And nullable arrays, so that was a Google Summer of Code project from last year. So Julia does not have missing data in the language by default like R does. So nullable arrays is one way to get this functionality. And so there were some performance complications with data frames in the past, some issues with type stability and some other things. Working with missing values gets tricky because you might have a missing value or a float 64, or you might have missing and some other object. So it's hard to give the compiler information on what you're actually giving it. So nullable arrays is this nice performant package, and it's now kind of the back end for data frames. And there's also quite a bit of stuff going on with other data tables structures, but I'll talk a little bit more on that. Another cool package is mixed models. So this is Doug Bates. So he is one of the R core members. So I think there's 20 or so R core members that have commit access to R. And so he is no longer working on R since he switched to Julia. But if you're familiar with R, he does the LME4 linear mixed effects models and the matrix package, which gives you sparse matrix support in R. Sparse matrix support is native in Julia. So we don't need anything like that. So I really like this quote that I came across a while ago. So as some of you may know, I have had a rather late midlife crisis and run off with another language called Julia. So that's Doug Bates in the Knitter Google group. So kind of getting him to switch, I considered kind of a big win for Julia. So he's contributed a lot to this Julia stat stuff. And yeah, he has this great mixed models package. And at JuliaCon last year, he was presenting. And he had a 10-minute lightning talk. And during his talk, he fit his model in Julia, and he said it took a better part of a day when he fit it in R. So he's obviously impressed with kind of the performance implications of switching to this fast, cool new language. So I think that's pretty exciting just to get the attention of, some older folks as well as the younger, people who like to try new stuff. So for general optimization, so there's an optimization package in pure Julia called optim.jl. Does a lot of cool stuff, and then there's also optimization packages that use backend solvers. So if you're familiar with like Mosaic and Gurobi, so those are pay things unless you have a .edu email address like I do. But so there's Jump and convex.jl. So convex.jl is Stephen Boyd's from Stanford's kind of disciplined convex programming implementation. But it's very, very cool. All right, so some of the up-and-coming things that I'm pretty excited about for Julia. So I'm working with this organization called Julia ML. You can look us up on GitHub and kind of see what we're working on. And so currently the only thing that's in metadata, which is the thing that allows you to just do package.add whatever package in Julia, is this losses package. So our goal is to come up with a whole bunch of abstractions for machine learning. So in this losses package, we have things like a L2 loss and an L1 loss, and things for quantile regression and support vector machines. And there's a whole bunch of abstractions, and then how do you get the derivatives of these things? So these are kind of we want to at least start by kind of implementing all like the primitives that we'd use for machine learning. So we have a losses package. We're also working on this transformations package. So a transformation could be anything from, I don't know, like an SVD or a PCA, or this could be just a linear predictor. So you can combine transformations with losses. And then we're also working on a penalties package, so you can add things like ElasticNet and SCAD or Lasso, or your favorite ones of those. And then you kind of play around with these primitive pieces that should be easy to work with. But I'm pretty excited about this stuff. In January, so on the Julia blog, I think Simon Byrne posted something about the statistics roadmap for Julia. So they got a considerable chunk of funding, and a big part of that was improving the statistics state in Julia. A big part of that is data frames, and I think that motivated part of the work for nullable arrays and some of those things. But so there are some very cool things, coming up. Which I feel like, so people were saying that several years ago, and we keep saying that over and over. But I think the closer we get to version 1, like the more cool things start to look, more stable. So we're getting there, even if we're not quite there yet. So some of the data table developments. So there's a Google Summer of Code project, which is called jplyr, a very subtle reference to dplyr and R. And that's the same student, David Gold, who worked on nullable arrays last year. Actually, I have a very quick. So he's actually implemented his own data table type, and then he's basically coming up with macros, which correlate well with the same verbs that are being used in dplyr. So I think that's a very cool tool. A very similar in scope is a project called query.jl, and they say you can filter, project, join, and group data from any iterable data source. So I've not tried query, so jplyr I think works really well. And then there's also was a talk at JuliaCon about this abstract tables.jl, which there hasn't been a whole lot of traction on, but I'm really interested in this idea. So the idea is you come up with the correct interface on how do you access table-like data. So you need to define for an abstract table type, how do I get a column, how do I get a row, how do I get subsets, and then you can write algorithms for generic abstract table types because you have the interface for accessing all these things already set. So David Gold, the jplyr guy, has an example or a quick demo of abstract tables that he's implemented. So yeah, it needs a little bit of traction, but I think it's a very cool idea, and I kind of hope it goes through. All right. So how can I use Julia alongside R and Python? So obviously there's a whole lot of things in R and Python that are already good, and we don't want to necessarily re-implement everything in Julia. So one of the main ones is pycall. So this allows you to call Python from Julia. This is heavily used. Some packages are basically just wrappers using pycall. So pyplot.jl is essentially just, calling straight Python. And there's also a scikit-learn.jl. One cool thing about this, so if there's a model in Python, you can call that, and then it also supports a whole bunch of Julia machine learning models. So you kind of call either one from Python or from Julia. So here is a quick example using using pycall, and pycall adds this pyimport macro, so I can import the math module, and then I can now just use that like normal Python. And it's a great thing that the syntax in Julia is close enough to Python, so it looks pretty much the same. Yeah, and here's a quick example of using pyplot, just plot randn, and even though I'm in a Julia kernel, this shows up in my Jupyter notebook. Things work nicely. All right, so I'm coming from the R world, like I keep saying. But so rcall allows you to call R from Julia, and you can also use Julia objects within R. So here is a very quick example. So using rcall, I'm making a random vector of 5 random normal 0, 1s, and then I have this R string macro, which basically is telling this to throw this thing into R. And then I'm also interpolating this value x, which is from Julia. So I have a Julia value, I'm throwing this into R, getting the absolute values, and then I'm returning this R object back to Julia. So this interpolation stuff is really very cool. I'm pretty excited about that. And oops. So in Julia, there are various REPL modes. So if you do a question mark, you get help. Oh yeah, I'm sorry. There we go. So yeah, question mark gives you a help mode, does a fuzzy search, and it also returns the doc string if you get it correctly. And then if I hit semicolon, I get the shell, and then rcall adds in R mode. So I can now load ggplot2 or, whoops, to use to Julia. And I can just kind of operate in R like normal, and then I can just switch back to Julia real quick, and you kind of have this great interop stuff. So one thing I was used to a lot more, so I was very comfortable with plotting in R and less comfortable with plotting in Julia. So this is easy enough to do in Julia. Is just to call the R-based plotting package, or if I want to be a little bit fancier, I can load ggplot2, and all this stuff just kind of works. So I'm interpolating these values that I'm providing from Julia, but I'm plotting them within ggplot2. All right. So now I'm going to talk about the Julia package that I think are contributing these really cool, unique things for data science. And so I keep saying this over and over, but I really like distributions. So basically, yeah, it just defines this great interface, and you know how to work with everything. So I won't harp on this too much, but it's really great for writing abstract code. Like you can write a Gibbs sampler that is very abstract and kind of switch out your priors really easily, and yeah, do a whole bunch of cool stuff. So the state of plotting in Julia was a bit messy for a while. So there's no base plotting structure quite in Julia. So there's a whole bunch of different plotting packages. They all have different syntaxes for how to use them. So it's just a little bit messy. So most people used Gadfly, and I think that's still probably the most popular one. But the Gadfly developer actually kind of went MIA 6-8 months ago or so. It has not been contributing. So the future of Gadfly, I think, is a little bit uncertain at the moment. But so I'm a very big fan of this package called plots.jl, and this is by Tom Breloff. He's another guy in the Julia ML organization, but he does a lot of really cool stuff. So basically what he has defined here is a smart unifying syntax for a whole bunch of different plotting libraries. So you don't really worry about which back-end plotting library is actually rendering this visualization. You just kind of worry about getting the syntax right for plots, and then you can switch between different backends. So you're basically just assembling a dictionary of arguments, and then for whatever backend, it figures out how to pass that dictionary as arguments into the backend. So you don't have to learn the separate syntaxes for pyplot or GR, or Plotly.js, which is interactive JavaScript, or Unicode plots, which plots right in your REPL, or PGF plots, which is for plotting in LaTeX. And there's more in the works. So here's an example of that. So I initialize a backend by the package name as a function, all lowercase. So I'm initializing pyplot, and then I'm plotting this value. I'm giving it a 100 by 2 matrix, and plots knows that I probably want to plot 2 series of length 100 rather than 100 series in length 2. And then I can immediately switch to the GR backend, and I plot this. Looks a little bit different. And then I can also switch to Plotly. The cool thing about Plotly is I now have all this cool interactivity, and I can, I don't know, play around with all my stuff, and I don't have to learn JavaScript, or I don't have to learn their specific Python API or Julia API. I can just kind of play around with things as normal, and I can just switch back and forth between backends. So I might want some cool interactive stuff while I'm playing around with data, and then when I switch to publication, I can just kind of switch the backend to pyplot and have a publication-ready visualization. So plots also supports a number of cool things that the backend itself might not support. So plots defines its own animation things. So it defines a GIF macro. So basically what this does is for every plot that I produce in this for loop, it's going to save a frame for every 10 of those. So I'm making a for loop of 1 to 1,000. I'm just adding a random normal 0, 1 to my plot, and then I'm plotting the frames, and I automatically get this cool GIF that I can present to you, and it looks nice. All right, so this is a bit shameless self-promotion, but this is the project that I'm working on mainly, called Online Stats. So this is streaming data algorithms for statistics, and kind of one of the main features is it gives you options on how new observations should influence your model. So here is a very quick example of this. So I'm giving a mean of an equal weight, so all these types that I define in Online Stats are parameterized by how new observations should weight the model. So an equal weight is going to do things analytically. An exponential weight is going to give it a constant weight of 0.01 for every single observation. So say I just have some data stream and I'm fitting these things. So here's one quick example of what this might look like. So say my model is actually changing over time, so I have the streaming data coming in. This red line is the equally weighted mean and this blue line is exponentially weighted. So we can see that this red line ends up estimating completely the wrong thing, and that's just because of this thing called parameter drift. Like our true parameters are changing over time. So if we're just calculating a mean, we're estimating the wrong thing, but we can just plug in a different weight into this thing and we end up estimating the correct thing with the exponential weight. So a mean is a very simple example, but the same parameter drift can occur in GLMs or support vector machines or anything else. So there's also ways to keep this idea of weighting observations, new observations differently. But a type that I'm very proud of is what I'm calling StatLearn. It's just statistical learning with regularization. And all these things are use stochastic approximation, but basically because they're using these approximations, they can kind of catch up with parameter drift as things are changing over time. But this can do elastic net type penalties with GLMs, quantile regression, support vector machines, Huber loss, and absolute loss regression. And this is kind of another example of using abstract code in Julia. Like I don't have different algorithms implemented for every single one of these. I've implemented these things once, and all of these like loss types have the same unifying interface that you can just pass these loss functions to. So again, abstractions are constantly the theme I'm talking about with Julia. But here's another cool thing that I think is going on called data streams. So this is abstractions for transferring table-like data from one source to another. So if you have a data frame and you want to pass that to a feather data frame, which is a cool backend or language agnostic way of passing data between like R and Python and Julia. And I think there's a number of other stuff. But Hadley Wickham and Wes McKinney of Pandas fame have been working on this. And then, so if you have a CSV file and want to pass that into a data frame, so basically he's come up with the correct language of how do you pass data tables from one source to another. And it's a very small package, and you just kind of need to define a few extra methods, and then all these abstract methods kind of take over and know how to handle your data from transferring one to another. All right, so we're very close to Duke. So some of you are probably Bayesians by osmosis. So Mamba is a very cool package for MCMC in Julia. So it's pure Julia, which I think is pretty unique. So when you're using things in R, you're probably calling winbugs or jags or stan. And those are great things. But if you want to figure out what's going on, you don't get to look at it in the language of your choice. You get to look at it in their languages. So Mamba is very cool, and again, has this very cool abstract structure, and you can kind of just throw around different pieces of priors and likelihoods, and things just work, and they're fast, and it's all in Julia, so if something's wrong, you can take a look at it really quick. All right, so those are the cool things that I've kind of discovered, and I'm very excited for in Julia. All right, so Julia has a great start. So it's been about 4 years since the first public appearance of it. There's fewer breaking changes with every release. So I've gone through the pains of 0.3 to 0.4, and I am now on 0.5. It was definitely easier 0.4 to 0.5, I think, than 3 to 4. And the developers have stated, basically, they want a release by the end of next summer, and they're planning on one more point release before that. And part of that is just to make room for deprecation warning. So there's going to be a 0.6, and then hopefully the next version is 1.0. So Julia is great for implementing your own algorithms. So I'm very hesitant to try overselling Julia, because I think it's great because it's perfect for me, because I'm implementing all my own research. I'm hard coding my algorithms. I don't have a whole lot of dependencies. But if you have a complex long-term project, it's going to need a lot more maintenance compared to Python, especially if you have a lot of dependencies, just because everything is still a little bit of a moving target, even though a lot has settled down. But that is all I have. Thank you.